Welcome back to the classroom. My name is Mr. Wong. Today we'll be looking at the historical methods to measure the speed of light. We're going to cover from times of Galileo all the way until the late 1800s, which we will designate as the historical period, and then we'll look at more contemporary theories or methods in our next video. So just to show you a bit about the history of the speed of light, you can actually see there are multiple variations in terms of the speeds. Now, obviously, these numbers will vary based on the type of source material you look into, but the very first person we're going to look into is Galileo Galilei, how he predicted the speed of light being 10 times faster than the speed of sound. And then we look at Roma, Huygens, Bradley, all the way to Foucault. And these are basically the historical time period we're going to focus on in terms of how the speed of light was determined. The main significance between the historical methods with the contemporary methods is the historical methods really rely on distance and time to measure light, while as the more contemporary methods, while some methods do use distance and time still, they also use interference patterns to do those kind of predictions.
So the first person we're going to look at is Galileo, and his apparatus was very simple. He had two lanterns, so himself and his assistant. They would have two lanterns separated from a hill, and they would try and perform it in a way where Galileo would uncover the lantern, time the time it takes for the assistant to see it, and uncover his lantern. So what they were trying to do is to see if there was a lag in between time when the lantern was uncovered and then when the second lantern was uncovered. And they were trying to time that difference in time. Obviously, light does travel very fast, as we know today. And so Galileo would try many different observations. They would try and increase the distance between the two hills. He even tried to use telescopes to help him with these calculations to try and increase that distance of separation. But as they continued, they found that it was near impossible to distinguish any difference in lag time, and the fact was it came back very simultaneously. So, unfortunately for Galileo, the actual experiment he performed wasn't very good at detecting any lag in time between lanterns being uncovered. And so he concluded that, or he suggested that light was not instantaneous but very rapid, to the point where he could not detect a lag time. And his hypothesis was that light traveled 10 times faster than the speed of sound, which, as we know, was not the case. And then we go to 1675 to Oleiroma, and he used the positions of the moons of Jupiter to help him work out the speed of light. Now, one of the common themes you would hear during this recall of the history of the speed of light is that a couple of these scientists weren't actually didn't set out to explore the speed of light straight away. They actually were trying to measure other things, and Roma was one of those scientists. Roma was trying to observe the eclipses of Io going past Jupiter. Io is one of the moons of Jupiter. And the idea was they wanted to determine the orbital period, so how long it took for Io to make one revolution around Jupiter. They found that the number was about 42 hours, 28 minutes, and 31.25 seconds. And so it kind of went like this. They were trying to see two things: how long it took for it to spin around Jupiter once, but also to measure the time it took for Io to pass Jupiter. So how long did that eclipse time when Io was behind Jupiter, how long was this particular time when observed? And according to Roma's observations, there are a couple things we need to take into account. Firstly, if Io does go behind Jupiter, no light can be reflected from the sun from Io back towards us. So we need to take into account the fact of Jupiter's shadow. For this observation to work, the Earth needs to have a clear line of sight towards Io. And so this is how the story goes. Roma made some measurements after 4 orbits of Io going past Jupiter, and so he observed the time of eclipse as the Earth was moving away from Jupiter in position A. So this is where his initial observations began. Then, in a separate observation, a couple of months later, a couple of orbits later, he then tried to measure the orbital period of Io going around Jupiter again. And what he found was there was a lapse time in this eclipse. So the eclipse occurring from Io past the Jupiter's shadow was about a 32 seconds longer than the position or at A than it was when he was observing it from position B. So let's try and understand this a little bit more and see how Roma interpreted this data he had. So he believed that the difference was due to the change in time it takes light from Io to travel to Earth. So this is quite significant because this is implying, or he was implying, that light had a finite speed. Okay, so light had a fixed number, or it's not simultaneous essentially. So finite speed of light. Ooh, that was pretty horrible, but you get what I mean. And so as the Earth is moving from position A1 to A2, you can think of it as the planet. The relative velocity of the Earth is moving further away from Jupiter as Jupiter is moving into its own orbit into the other direction. So as our Earth from position A1 moves further and further away to A2, it takes the light from Jupiter longer to reach Earth because of this change in velocity. So the relative velocity is moving further away from Jupiter. So the light, because it has a finite speed, needs to take longer to catch up and reach Earth at A2. Now, with his observations changing, let's have a look at position B. In position B, the Earth is moving closer towards Jupiter. So its relative velocity is moving closer to Jupiter. And so it's almost, you can almost imagine it as two cars are moving towards each other. If two cars are moving towards each other, from the observer's point of view of one of the cars, it will appear that the second car is moving faster towards you. So one car is moving at that, and then you have another car. It would appear like you're moving a lot faster towards each other. Same idea here. When he was at position B, or when the Earth was at position B, Roma discovered that the eclipse was a lot shorter. So the time for him to see that eclipse occurred at a shorter period of time. And so he concluded that light took less time to reach him when he was in position B1 moving to B2, in compared to position A1 going to A2, where light took a lot longer to reach position A compared to B. Okay, so if we try and put a bit more detail towards this. So basically, Roma estimated that when the Earth was nearest the Sun, say position A1, the eclipse of Io would occur 11 minutes earlier. So he would see the eclipse 11 minutes earlier than predicted based on the average orbital period. Now, the orbital average, if you remember, was roughly about 42 hours, 32 minutes, I do believe. I could be making this up. And about 31.25 seconds. So that was the average we kind of talked about earlier in this lesson. What he predicted was at A1, it would come about 10 minutes earlier than the average recordings that he did throughout the entire series of observations throughout the year. He also believed if the planet was at A2, the eclipse would be, and this is about 6.5 months later, the eclipse would take about 11 to 10 minutes more than the average for the eclipse to occur. Okay? So for them to actually see the eclipse, instead of say 42 hours and 32 minutes, if we add an extra 11 minutes, we'd say we'd see it in 43 minutes. So that was what Roma was implying from his investigation. He invited some scientists from the Royal Society, and they actually witnessed the eclipse took about 10 minutes longer to occur in comparison to what the average was known to them at the time. So it showed that Roma's predictions were very accurate. And what Roma also predicted was you could actually work out the speed of light because of this argument. So because light takes longer to travel from A1 to A2, we have a distance. Okay, so that's the diameter of the Earth. He believed, now that we know that it's 11 minutes earlier from A1, so we have 11 minutes here, and it's 11 minutes longer at A2, so 11 minutes here. So he predicted in total the time it takes for light to travel from A1 to A2 was roughly 22 minutes. And so if he knew the diameter of the Earth's orbit, so the Earth orbiting around the Sun, and the time it takes for the light to travel from A1 from one side of the diameter to the other side, he could work out what the speed of light was. So this is the summary page. What we were talking about was the formula. So the formula they used was the diameter of the Earth's orbit divided by the time the light had to use to travel the Earth's diameter. This was the value that was measured or calculated at the end by Huygens, who was reading the works of Roma at the time. So let's just go back and conclude what the findings of Roma's was. That speed of light is finite. The time for light to travel from one side of the Earth's diameter to another is 22 minutes. Now we know that this value that was calculated at the end is very, very far off the current accepted value for the speed of light. That's because the time that was predicted for light to travel across the Earth's diameter was actually slightly off. It was actually a lot lower, so the actual time between was actually a lot lower, more closer to about 16.7 minutes. And the other thing was the actual diameter, of the Earth's orbit, the measurements they actually had at the time were not as accurate as the ones that we have now. And so these two discrepancies cause this mass discrepancy in the final answer of light. But the important thing is now we do know, or at least from Roma's evidence, that we can imply for sure that the speed of light was finite. Obviously, you need a couple more scientists to show and prove that, but that was the starting point that really directed us that light was finite in speed. And we also know, obviously, how his experiment occurred. Okay, the next person we're going to look at is a guy called James Bradley from England, and he used the changing appearance of stars as his method of calculating the speed of light. Again, he wasn't actually trying to find the speed of light, he was just trying to understand a phenomena called stellar parallax. So, have a look at this. If a star is orbiting, or let's say Earth is orbiting around the Sun, we have a thing called stellar parallax. And this was looked at by Robert Hooke. You might remember Robert Hooke as the guy who created the microscope. But the principle of parallax is fairly simple. If the Earth is rotating around a celestial object, say the Sun, then we will see an apparent movement in the stars in the sky. Okay, so we know that stars don't change their position. However, what we do know, or what we now know, is that their positions in the sky changes because of the observer changing their position. Because our planet is rotating around the sun constantly, then our position of where we see the stars also changes because of the Earth rotating around the sun. So that's stellar parallax. And he was trying to understand more about this change that we see in the sky. What they found, though, or what he found, was something slightly different. He found a thing called stellar aberration. And so, aberration actually looks at a fairly slightly different principle, that not only does the star go sideways, but it can also go backwards and forwards. Let me show you what that looks like. So if we look at this diagram here, or this animation, it looks like the star is going from left to right over here, from left to right. However, they're not only just going left to right, they're also going closer or further away from us. And that's because stars and the planet are not flat, so they're not in the same horizontal plane as each other. The stars will be at some angle towards Earth, and depending on what angle the Earth is looking at the star might look steeper or it might look more shallow in the sky, which causes this effect where it looks like it's looping in and looping out. And so what's the significance of this? Well, we know from when we're talking about frames of reference and speed of light that the reason why we're seeing this is because the object, the Earth, is moving in one direction. So we have Earth moving in one direction. We have light moving down. Let's just assume light is just moving down. Now, what we know from relative velocity in 2 dimensions is from the Earth's perspective, the speed of light looks like it is coming down this way towards us in this diagonal position. A good way to interpret this or imagine this is, say it's a really rainy day and rain is falling down and you're holding an umbrella and you are just stationary. If you look up, the rain will look like it's just falling down onto you. Now imagine you start walking forwards, okay? If you start walking forwards, your umbrella is making contact with not just the rain on top, but the rain that's just in front. So according to you, you try and tilt your umbrella slightly because it feels like the rain is coming at you at some angle down like so. And so that's kind of the same thing that was happening with our observations of stellar aberration. And what James Bradley did was he used the angle that was created by the relative velocity between the speed of light and the speed of the Earth's motion, found that angle, and he used that to work out what the speed of light would have been. And the consequence of that was obviously it showed that light had a finite value, used a stellar aberration to calculate the speed of light by knowing that the speed of the Earth around the Sun and knowing the angle of aberration. So he used sort of trigonometry. So if he could measure, so if we drew that out again, so that's C, that's v of Earth. If we knew what the velocity of the Earth was, and we could calculate or we could measure the angle that the Earth was making to the star, so our star's here, Earth is here. If we can measure this angle and we can measure the velocity of the Earth, then we should, by definition, be able to work out the speed of light that way. And we worked it out, or James Bradley worked it out to be this value here. And so that's just to show you how light has a finite value, and also the speed of light in a vacuum was traveling at this velocity. So that was his contribution. The next person we're looking at is Farah, or probably, I don't know actually how to say his name properly, I do apologize. And his apparatus is very simple. So he had a light source that would shine towards or shine through. He had a light source that shined through a slotted gear and it would hit a mirror. What would happen then is the light from that mirror would strike back and hit the slot. If he spun the slot really quickly, or if he spun the slot really slow, the light would just go straight through and he could see the light very transparently. If he rotated the slot faster, what happened every now and then was the slot would block out the light. Okay. If we put this in a bit more detail, so the actual distance between the gear and the mirror was thought to be about 8 kilometers, and he began rotating it very slowly so that the light could just go straight through the gaps of the slots. When he increased that speed, so he kept on increasing the speed until there was periods of time where he could actually see there were little gaps in between his observations, so it wasn't transparent light coming through. Some parts of the light was actually being blocked off by the gear, and that actually stopped him from seeing it. So he thought to himself, if he can work out the frequency at which the gears were rotating, and work out how many gears, so how many gears was, or how many slots was on his gears, he could work out the rotation rate. So he could work out the period of the gear. And from there, if he worked out the distance, so the distance was 16 kilometers. So if you knew distance and you know the period of the gears rotating, he would be able to work out the speed of that light source. And this was quite important at the time because until then, most of the observations were not very precise and not very reliable. What essentially he did differently is being able to do this in the lab where he could actually perform a reliable and valid experiment. The significance of his experiment is it provides a more reliable and valid method of measurement. There are many more scientists that came after him that used a similar method to his and just did some additional modifications. So he used a rotating rate. So by using the rotation rate of the disk and the fraction of the circumference of that disk, he worked out the period of rotation. So he worked out the period of rotation of the gear, and by determining the time of that in 16 kilometers, that was his distance. The video, like I said, is a great explanation of how all the calculations came to be. So if you do want to understand the calculations, have a watch of that video again. The speed of light in a vacuum was determined to be this value here. So it was a bit higher than what James Bradley had, but like I said, in terms of repeatable experiment and getting rid of other variables, this was a very good starting point. And then we had Léon Farquhar, and he basically adapted the gears experiment. However, instead of using a gear, he used a rotating mirror to measure the speed of light. And so by rotating the mirror, he could detect the time it takes, or the angle at which where the light hits the rotating mirror, hits the stationary mirror, and then waiting for that light to hit the rotating mirror, and then come back and get detected by the observer. The idea was if he knew the particular angle at which the rotating mirror would reflect back onto the observer, he would be able to work out, obviously, theta, 2h. H is just the distance between the stationary mirror and the rotating mirror. And so that could help him work out the change in time. And using that, he could work out the velocity of light that way. And so this is a slightly better illustration of this. So you have the light source hitting the rotating mirror, fixed mirror, and then the fixed mirror pushing back onto the rotating mirror and detected by the light source again. Okay, and we have theta as the angle in which that reflection was occurring at. So when we substitute it into our formula here, delta theta over delta t, so change in theta over change in time, times 2h over theta. And that led to the speed of light being calculated there. Then we had Albert Michelson, who again upgraded the rotating mirror. From one mirror, he had 8-faced mirror, and he would rotate that mirror around. A similar idea, he actually increased the distance to 63 or 36.5 kilometers, sorry, and that's how he went from there. Okay, so some of the distances do slightly differ, but let's just say it's around 36-35 kilometers. So the light source would hit the rotating mirror. The rotating mirror would then hit the stationary mirror 35-36 kilometers away, and then it would reflect back to the rotating mirror. Now, depending on the angle the mirror was at, sometimes the light would be shifted away from the observer or shifted too far in the opposite direction. He was trying to find the rate, so this spinning rotator, he was trying to find the rate of speed that this rotating mirror had to spin in order for the light to just hit the perfect spot and hit the observer. So he was trying to find the frequency in which the rotating mirror needs to turn, so that when the reflected ray from our stationary mirror hits this rotating mirror here, it can be observed by himself. And so by finding out the rate of rotation, he could then work out the speed of light because he already knew the distance between the stationary mirror and the rotating mirror.
And that concludes our lesson for today. Remember, our focus was to look at the historical methods of which light was being, or the speed of light was being measured. So we covered through Galileo, Roma, Bradley, Fresnel, and Foucault. So there were the methods that we looked into. In our next lesson, we are going to be focusing on the contemporary methods in which speed of light is being measured by, and what is the actual significance that has to our current understanding of time and distance. So until next time, take care.